On our program this week, the operation of a nuclear reactor, safety in an atomic power station, and the management of radioactive waste. Did you know that nuclear reactors have been operating on Earth for thousands of years? This startling discovery was made by French scientists when analyzing uranium in an African mine. Geological evolution and the emergence of oxygen contributed to the creation of these natural reactors, lodged deep in the Earth's crust. Much later, man would recreate the feat.
In the 40s, oil, coal, and waterways supplied most of the world's electricity. A new source, however, emerged from the physics laboratories to become one of the most important of all: nuclear energy. The very first nuclear reactors, which were called atomic piles, did not provide electrical power. But these modest facilities helped us uncover the secrets of nuclear phenomena and learn to control them at will. Before long, the familiar giant concrete and steel buildings that housed nuclear reactors began going up. There are many types of nuclear reactors. The most commonly used worldwide is the pressurized water reactor, which we will be describing here. This type of reactor is based on the same principle as all other reactors, namely nuclear fission. That is the property some atoms have to divide, emitting a great amount of energy. All atoms consist of a nucleus surrounded by a cloud of electrons. That nucleus contains two other types of particles in varying numbers: neutrons and protons. These particles are held together by a very powerful force physicists call binding energy. In nature, most atomic nuclei are stable. Lead will always be lead. However, there is one naturally occurring nucleus, just one, which can be induced to fission by being struck by a slow-moving neutron and liberating part of its binding energy. It is the uranium-235 nucleus. The number 235 corresponds to the sum of protons and neutrons in the nucleus. Other man-made elements, such as plutonium-239, can also undergo fission. Uranium's 235's fission is not spontaneous. For it to break up, an incoming neutron must collide with the uranium nucleus. The nucleus then breaks up. It releases energy, along with 2 or 3 other neutrons. As they fly off, these neutrons may collide with other uranium-235 nuclei, initiating fission again, liberating further neutrons and energy, and so on. This is the famous chain reaction, which constitutes the source of energy in all nuclear reactors. To facilitate the chain reaction, pressurized water reactors use a fuel in which, by way of a complex process, the amount of uranium-235 has been increased. It is enriched uranium. Uranium-235 consists chiefly of uranium-238, an atom which does not have the property of dividing. If natural uranium were used, only a fraction of the neutrons would encounter uranium-235 nuclei in passing. The chain reaction would occur with greater difficulty. Also, the liberated neutrons travel at very high velocity. So high, in fact, that there is little chance of their colliding with a uranium nucleus. To enhance the probabilities of collision, the neutrons have to be slowed down. This is done with a moderator, a substance that slows neutrons down without absorbing them. In a pressurized water reactor, the water is the moderator. The chain reaction occurs in the core of the reactor, a steel tank filled with pressurized water. The fuel is in the form of pellets inserted into metallic jackets called pencils. Water circulates between the pencils. It slows down the neutrons going from one pencil to the next, therefore initiating a self-sustaining chain reaction. But the water circulating in the core of the reactor does not only act as the moderator, it makes it possible to control the temperature of the core and keeps it from overheating. This water, also called primary water, has another crucial function. Heated by the fuel, it penetrates into a myriad of tubes, the steam generator, around which water also circulates. The water circulating around these tubes, secondary water, evaporates. The steam is relayed to a huge turbine that turns an alternator which generates electricity. The steam is not expelled into the environment. It is condensed on contact with a third circuit, the coolant circuit. A pumping station feeds cold water from the sea or a waterway into this tertiary circuit. The water in each circuit then returns to its starting point, the tertiary water to the sea, the secondary water to the steam generators, and the primary water to the reactor vessel. These three circuits exchange heat, but never, under normal circumstances, water. This reduces the chances of contaminating the environment, since only the primary water, in contact with the fuel elements, is radioactive. Unless there is a leak, that radioactivity will not be transmitted to the secondary water. Nuclear energy has its drawbacks, but in terms of efficiency, it is unsurpassed. The fission of a single gram of uranium-235 produces as much energy as 2 tons of coal burnt in a classic thermal power station.
The safe operation of a nuclear power station poses a major challenge. It can only be done by multiplying the barriers between the atomic reactor and the environment.
Hiroshima, August 6, 1945. On that day, humanity discovered with horror the awesome power of the atom. Fortunately, the physicists also learned how to harness this formidable energy for peaceful purposes. Great strides have been made when you consider that nuclear energy now supplies almost 20% of the world's electrical production, and that, generally, its effects on health and the environment have been minimal. There have, of course, been exceptions, such as the terrible accident at Chernobyl. Undeniably, the safe harnessing of the atom calls for a multitude of complex and costly preventive measures and techniques. The safety of a nuclear power station is based on a concept called defense in depth. The objective of defense in depth is to reduce the likelihood of any accident liable to contaminate the staff, the environment, or the population. One of the methods used consists of erecting a series of barriers, as insurmountable as possible, between the radioactive reactor core and the outside world. Pressurized water nuclear power plants have 3 such barriers. They are arranged somewhat in the manner of Matryoshka dolls. The first barrier consists of airtight metallic sheaths in which the fuel pellets are sealed. The second barrier is an over 20-centimeter thick steel tank. It is in this tank, which is filled with water and closed with a heavy lid, that the fuel pencils are stored. The third barrier is a concrete wall, close to 1 meter thick, called the reactor building. The reactor building is designed to withstand major external accidents, such as a plane crash or a major earthquake. According to the experts, This triple confinement eliminates just about all risks of contaminating the environment. For any radioactive elements to get through the 3 barriers to the outside, a simultaneous triple leak would have to occur. There is very little probability of this ever happening. A nuclear power station also continuously produces slightly radioactive residues. But these liquid and gaseous tailings are decontaminated and strictly controlled before they are released into the environment. Inside the plant, numerous measures are taken to ensure the staff is well protected. As a matter of control, the employees undergo systematic checks for contamination and radiation exposure levels. But nuclear reactor security involves more than monitoring tailing emissions or people's exposure to radiation. It also aims at reducing the chances of serious accidents. To do so, the reactors have to be equipped with systems that will slow down or stop the chain reaction. Control rods are inserted into the core of the reactor at various depths. The rods absorb the neutrons which normally keep the chain reaction going. This either slows the reaction down or stops it completely. The reactor can either be stopped automatically or by hand from the control room. If the control rods fail to perform as they should, it might cause a dangerous runaway chain reaction and an accident. In this type of power station, an accident could also occur if the water which cools the reactor core were suddenly to stop circulating. In the worst-case scenario, the temperature of the fuel would shoot up to a critical point, meltdown of the core. This is the worst disaster that could possibly happen in this kind of power station. Indeed, the contaminated water contained in the reactor vessel would begin to boil and cause the vessel to explode. A reactor core meltdown occurred once in the United States, but fortunately no radioactivity was released into the environment. A very promising technique consists in using a powerful computerized simulator to visualize and study how a nuclear reactor behaves in dangerous situations. This system reproduces in real time the behavior of a real reactor in all sorts of situations. From a control station, various types of accidents can be simulated, such as a leak or a casing failure. Another screen, called an educational station, makes it possible to visualize by transparency part or all of the reactor and to observe the physical phenomena which occur inside it. From the control station, attempts can be made to bring the situation under control. For example, to maintain the temperature or pressure of the reactor within a safe margin. This kind of tool enables scientists to devise ways to counter every possible catastrophe.
Now, every country which has developed a nuclear industry is grappling with a delicate problem: how to dispose of the tons of radioactive waste that continue to pile up.
Nuclear energy was only discovered a few decades ago, but already it has countless uses. To date, it is one of the best controlled forms of energy. But the picture is not entirely rosy. Like all human activities, nuclear energy produces waste. And to date, the problem of nuclear waste disposal remains unsolved. What makes nuclear waste so hazardous is its radioactivity. A body is radioactive when its atoms are unstable. In seeking to return to their stable state, the atoms liberate radiation in the form of particles or energy. That radiation is highly toxic for all living things. Beyond certain levels, it can cause cancers and mutations, for example. Fortunately, radioactive elements are not immortal. By emitting radiation, they become new elements whose radioactivity will eventually peter out. The time required for the activity of a given radioactive element to decrease to half of its initial value due to radioactive decay is called a half-life. Half-lives vary substantially. They can range from a few fractions of a second to several billion years. The most dangerous elements have an intermediate half-life. For instance, iodine-131 has a half-life of 8 days, and plutonium-239, 24,000 years. As a rule, an element's radioactivity decreases very gradually. It is estimated that it takes some 12 half-lives before the element ceases to pose a serious threat. There are various types of nuclear waste, depending on their origin and their activity. For the most part, they have little or average activity and are short-lived. They include, for instance, clothing or gloves, bulbs or hospital needles. While they represent 95% of the total volume of nuclear waste, these residues emit less than 1% of total radioactivity. Their conditioning no longer poses a problem. They can be stored, for example, in concrete containers and arranged in stacks somewhat reminiscent of the grave mounds of old. The nuclear waste causing the most concern is the highly radioactive waste. These residues account for less than 1% of the total volume of nuclear waste, but they emit 99% of all radioactivity. And especially their lifetime can span dozens of thousands of years. This waste comes chiefly from the spent fuels of nuclear power stations. In a power station, a fuel seldom lasts more than 3 or 4 years, after which it ceases to be effective and is replaced. The problem is how to dispose of this spent fuel. Some countries recover it through reprocessing. Spent fuel not only contains waste, but also fissile materials, which can be recycled into fresh nuclear fuel. Reprocessing separates these useful elements from the waste. First, the spent fuel is shipped to the reprocessing plant in sealed containers or transportation flasks. These flasks are highly shock resistant. They block any radiation emissions from their contents and allow the intense heat generated by the fuel to be expelled. Unloaded from the transportation flasks, the fuel elements are stored in a huge pool beneath a thick layer of water. The water serves a dual purpose. It blocks and cools any radiation generated by the spent fuel. The elements spend at least 2 years in these pools. This form of storage gives the short half-life nuclear waste in the spent fuel the time to decay. Then a special process, remote controlled from an immense control room, separates the elements that are still useful from the nuclear waste. This process consists of shearing the spent fuel elements. They are dissolved in nitric acid and their components separated with a solvent. The waste is then vitrified, that is, immobilized in glass, inside sealed steel containers. The containers trap the radioactive waste and retain the radioactivity without, however, eliminating it. For now, these containers are stored in ventilated concrete pits under a 1-meter thick floor that seals the radioactivity. These containers are indeed extremely dangerous for all life forms. But since this waste will remain radioactive for thousands of years, it is imperative that long-term solutions be found. At present, the preferred solution would be to store the waste deep down in stable geological layers that are as impervious as possible. Tunnels would be built in which the conditioned waste would be buried for all eternity. But this solution is far from satisfying everyone. Indeed, what assurance do we have that thousands of years from now, future generations will know where these dumps are located and how very deadly they will still be?
Nuclear energy, aeronautics, informatics, all fields where the level of risk is equal only to the complexities of technology. In the face of these systems, more and more, man is becoming the weak link. No wonder we are wary of these achievements, however brilliant.